So the story actually begins years ago when I was tutoring mathematics for levels from grade school to college, university, and some of the sessions would be one-on-one tutoring sessions, and some would be in groups, groups of 5-6 students. And these group sessions would cover subject matter that's more advanced than what students are covering in school. For example, one group can have the youngest student in grade 7 and the oldest student in grade 11, and the material covered would be just one topic more advanced than what the grade 11 student is covering in class. And all of the students in the group would actually be at the same mathematical level. And if that's surprising, I can tell you it's certainly possible for someone of grade 7 age to have a grade 11 level of mathematics. If they are taught to do it, then they will be able to do it. And what I noticed is that students were actually lacking a lot of foundational mathematical skill sets. Certain elements of mathematical intuition, things like the multiplication tables, doing strategic calculations, and it's in these certain areas where students would often become frustrated, even though they actually had more advanced concepts understood and they found it interesting and so on. So I created certain game-like exercises to help them learn. So the most common exercises we would do just to warm up at the start of class was as follows. With a regular deck of cards, okay, what the picture you see in front of you is actually the Quant deck that was invented later. It started off with a regular deck of cards where I would draw first two cards, just two cards, and in the group, whoever says the answer of multiplying those two numbers first would get those two cards. Those are their points. Okay, then I would draw the next two cards. Whoever multiplies those numbers first, says the correct answer, gets those two cards. That's their points. The multiplication is done in their head, no paper, no calculator. And so we would do a few rounds like that. Then I would draw three cards. Now they have to multiply three cards in their head. Whoever gets the right answer takes the cards. That is their points. A few rounds of that. Now we draw four cards. They have to multiply four cards in their head, and so on. So with two cards, this is just the multiplication table, right? It's a quick way, easy way, to get students to memorize this. Once you get into 3 cards, 4 cards, 5 cards, now they have to be strategic about it. Okay. By the way, how we would do this is jacks would be 11, queens would be 12, kings would count as 13, and aces were 1s. Now, also jokers would be 0. Now, for this example, okay, so say you have to multiply 13, 6, and 11 in your head. What do you do strategically? Well, let's save the easy stuff for last. 11 is almost 10. We're just going to save it for last. Let's do 13 times 6 first. If you don't have it memorized, well, 13 is just 10 plus 3. Okay, so 13 times 6 is 10 times 6 plus 3 times 6. So we have 60 plus 18, which is 78. Now we need 78 times 11. Well, 11 is just 10 and then another 1, right? So 78 times 11 is 78 times 10 plus another 78. So we have 780 plus 78, 858. Right? So these calculations can be done in your head, and with enough of this kind of practice, students would get really good at it. They could multiply 4, 5, 6, 7 cards in their head. And what would sometimes happen is, we lay out, say, 6, 7 cards on the table, and students are thinking about it so intensely. And they can't just blurt out answers till they get it right. If they blurt out the wrong answer, they are out for that round. So what you have is you have complete silence, and students are so intensely thinking about this that some would get up from their chair, walk around, waving their fingers in front of their eyes to visualize the calculation that they're doing. And it would improve not just their multiplication tables, obviously, but many more advanced things, right? There's strategic thinking, right? We're talking about very large numbers with many digits that they would be calculating. It would improve their mathematical intuition, which is really just an understanding of how numbers work. Another exercise is adding a large amount of numbers in your head, and how to do that quickly. Okay, strategy also comes in. So for example, for these 8 numbers, one strategy is look for sets of 10. Okay, so for example, in the top row, we have a 2 and an 8. That's a 10. We also have just a 10 on its own. On the far left, we have a 7 and a 3. That's another 10. In the bottom, in the middle, 13 and 7. That's 20. That's 2 10s. Right? So that's 3 10s altogether plus another 20. That gives us 50. And then another 2 in the bottom right. So 52. Right? So again, all this strategic thinking, developing mathematical intuition. And mathematical intuition helps with understanding so many things around us. Just understanding how numbers work, the relationships between them. So for example, I was talking to a friend of mine recently. He talked about he mentioned this joke theory that the longer a debate about politics continues, the higher the probability that someone mentions the Second World War. And I told him that, I'm sure that theory is absolutely true. But in fact, that is true for every single subject matter in any conversation. Okay? The longer any conversation goes, the higher the probability that any particular subject matter will be brought up. Okay? And this is just a phenomena based on the fact that however statistically unlikely something is, the more opportunity you give for it to happen, the higher the probability that it will happen at least once in that span of opportunities. For example, if you roll 2 dice, the probability of rolling 2 ones is very low. It's 1 out of 36. But if you keep on rolling 2 dice, the probability that at least one of those rolls will be 2 ones, it gets higher and higher and higher with the number of dice rolled. If someone rolled 2 dice 1,000 times and none of those rolls were 2 ones, well, that's very strange. Then I would suspect that one of those dice does not have a 1 on it. So any subject matter, let's say you're talking about sports, the probability that cheese will be brought up during 1 minute of a conversation about sports could be a pretty small probability. But the longer that conversation continues, the more minutes have gone by, the higher the probability that at least during one of those minutes, someone mentioned cheese. Okay? And so the longer the conversation goes, the higher the probability that cheese will be mentioned at some point. Okay? Similar phenomena is, sometimes a conversation will move from topic to topic and eventually return to the original topic of conversation. And people say, oh, we went full circle. What are the chances we got back to where we started? The chances are actually not that small. If a conversation goes on for a long time, the longer it goes, the higher the probability that at some point that initial topic that started the conversation will be brought up again. So students would develop this kind of mathematical intuition, and I noticed, well, this is really helping them. Then students started asking, can we play this at the end of the class as well, right? I would do it at the beginning as a warm-up. Okay, my idea was, let's make math class more like gym class. Okay, because what we did in gym class when I was in high school, it's mostly playing games, and people liked it. It was fun. A lot of people, they didn't find math class to be that fun. But for me, math is also like playing a game. It's just solving puzzles. That's what it is to me. So to me, math and gym was the same, and I thought, okay, well, let's try to do that. Let's make math class more like gym class. And so start off with a warm-up, right? A game like this. Then students would ask, well, can we play it at the end? The last 5-10 minutes at the end of class. I'd say, sure. We would do that. Then the class is over. The next class comes in. The next class, they know this game. Okay, we're going to do this warm-up. The previous class says, can we stay and play the game for the first 10 minutes of the next class? While they're doing their warm-up, we want to play with them as well. And I would say, sure. So we would have a larger group playing. And I thought, okay, well, these are teenagers. They just finished this, evening extracurricular math class that their parents are making them take. They now have free time. They could do whatever they want. What do they choose to do? They choose to stay and learn more math. Well, that means something, right? That something right is happening here. One story that a student told me was she was about 14. She was in a jewelry store with her mom, and she pointed just at some piece of jewelry and said, "Hey, can I have this?" It's not exactly a kid asking for a chocolate bar at a corner store, right? It's a piece of jewelry. And the mom said, "You see that price there? That's not the real price. Okay, the real price is that plus another 13% tax. So if you can tell me, if you can calculate it in your head exactly what the real price is, correct to the final cent, then I'll buy it for you." And the student, she walked around the jewelry store for the next few minutes, imagining, waving fingers in front of her face, and then she told the mom the answer. And it was the right answer. And the mom was pretty surprised and impressed, and well, she said she'd buy the jewelry, so she had to do it now, right? And she got her that piece of jewelry. So I noticed, okay, this is a quite effective, exercise, set of exercises, and I started thinking, okay, well, let's improve it. So one thing is that there were some flaws with using a regular deck of cards for this. One flaw is that the numbers are small in an ordinary deck of cards, right? You have, people sitting around a table, you draw a number of cards, they have to squint to see what the small numbers are. That could slow them down if it's, a game where you want to say the answer before someone else does. The other issue is that students would have trouble remembering, what number is a jack? What number is a queen? Right? Is it 12? Is it 13? What about the ace? Is it 1? Is it 14? So that would slow down students as well. There's also 4 aces, which is 4 ones, which is a bit much. Okay, it's fun to have ones and zeros because they make a calculation a lot easier, but you don't want to have it too much. So I created a new deck specifically for these educational games called the Quant deck, and the numbers are larger. There's no face cards. You actually see the number there, and it's a 13 instead of a K. There's less ones, right? There's only 3 ones. There's 2 zeros in it as well. Zeros are a great learning opportunity for some special cases. If you have to multiply a string of numbers, one of them is a 0, right away the answer is a 0. And for more advanced subjects, zeros come in useful as well. I'll talk about that a bit later on. And then I started creating more advanced exercises for more advanced subject matter with these Quant cards. So exercises for statistics, for arithmetic, for physics, for finance. I started using these exercises not just in tutoring, but in more advanced settings, in teaching, degree level mathematics as well. And a colleague recommended to me that, why don't you do a study on this, on the effectiveness of teaching with these cards, right? From your personal experience that it helps, but do an academic study. So I thought, great idea, and did a study on statistics, okay, teaching degree level statistics with Quant card exercises. So I'd already been doing Quant card exercises and statistics by this point. Now it was just a matter of doing a statistical study, a academic study. So the study design was as follows. I was teaching 3 sections of the same introductory statistics class, and 2 of those sections were the experiment group. So for some topics, they did Quant card statistics exercises for those topics. One section was the control group. So they covered the same topics in the same order. They had the same assessments, but they did not do any Quant card exercises. Instead, they just had more examples on the board. Now, out of the 11 topics covered in the course, 4 topics had Quant card exercises, associated with them for the experiment group. And there were quizzes that were approximately 1 week after the quant card exercises that were specifically on the subject matter of the quant card exercises. The control group had those quizzes as well around the same time. Just the control group, rather than having quant card exercises for those topics, still covered those topics at the same time, but again, more exercises as examples on the board instead of quant card exercises. Now, initially, the intention was to cover 7 topics with quant cards for the experiment group and have 7 of these quizzes. But this was winter 2020, in the middle of the semester, the pandemic hit. So actually there were 4 topics covered with quant card exercises and a quiz that followed. There was another 1 topic covered with quant card exercises, but there was no quiz after. And that's it. So another 2 topics that were intended to be covered with quant cards were not, because by that point everything was online because of the pandemic hitting. So the data that was collected was the average grades for these quizzes, the average grades for other assessments as well, and survey results where students were just asked about their classroom experience. These quizzes were bonus quizzes. They were intentionally rather difficult. So just for doing the quiz, students would get 1 bonus % on a future assessment, and if they actually got perfect on the quiz, then they would get 2 bonus %. So there was the incentive to do well on the quiz, even though it's a bonus quiz. So the 4 topics that were covered with quant card exercises and had quizzes for them was mean, median, mode, standard deviation, percentiles, box plots, and probability and frequency tables. So for the first 3, mean, median, mode, standard deviation, percentiles, and box plots, the kind of exercises were rather similar. The class would be divided into groups. Each group would be dealt a set of cards, and they have to do various calculations. So for example, what's the mean value of the cards in front of you? What's the standard deviation? If you had to create a box plot representing the data that the cards in front of you show, what would that box plot look like? So different groups would have different answers. Effectively, different groups have a different sample, whereas the population is the entire deck. Okay, now we know what the deck looks like. We know what the population mean is. We know what the population standard deviation is and all this. But the results that students have would be different, right? Because they only have a sample of the cards in the deck. Then we would talk about it in front of the class. What are the different results that different groups had? Why did they have those different results? Did they have outliers? And so on. For probability and frequency tables, the cards were used to generate random numbers for frequency tables. Also, this kind of group work would be done with probability, where students would be dealt a set of cards and asked, well, what's the probability of, say, based on the sample in front of you, what's the probability of drawing a card higher than 5? And how does that probability differ from, the true probability of drawing a card higher than 5 in the entire deck? So one example for percentiles and box plots is, say you have 4 groups, and each group is given 10 cards, right? So here on the left-hand side, you have group 1 and the 10 cards given to them underneath. Group 2, the 10 cards given to them underneath, and so on. And based on the cards given to them, they have to create a box plot. So what does that mean? Well, they need to calculate the mean value. They need to calculate the median. They need to calculate the interquartile range. So the interquartile range is where the central 50% of the data is. Okay. So for example, for this blue box plot here, the box represents the interquartile range. So it's from just under 5 to just under 9. Okay, so the central 50% of the data is within that range. 25% of the data is above it, up to the maximum, which this top whisker shows, and the lower 25% of the data is below it, up to the minimum, which this whisker shows. The line in the middle of the box is the median, the X is the mean value. So we have 4 different groups. They're each dealt 10 cards from the same deck, and we have 4 different box plots. That's the result. So first off, you just did 4 examples. You have the results of 4 different examples and the time that it took to do one example, right? And so already you can discuss these 4 examples, the difference between them on the board. If we take the blue example on the far left and the yellow example on the far right, they look pretty different, right? The group 4, their box plot, the yellow one on the right, it has a much larger range. The range is larger, the interquartile range as well is larger, right? The data is just, it appears to be significantly more widespread, but it actually comes from the same deck. It's a sample from the exact same deck as group 1's. Okay, so this class discussion could also be used to launch into a topic of statistically significant difference. Okay, so 2 different samples can show you a different result, but is the result different enough that we say it is statistically significant, that it looks like these 2 samples are actually taken from different phenomena? Or is the difference close enough that it's actually, it could be attributed to just random variation in the data? Okay, so that's an example of a kind of discussion that can arise after analyzing these results. You could also discuss, what outliers, what abnormalities in a sample could lead to a result like a box plot looking unusual. So this is the assessments that existed in the course, and the experiment group's average grade, the control group's average grade, and whether the experiment group had a larger average grade than the control group. So what we see is that for all but 1, so we have 9 assessments here, for 8 out of 9 assessments, the experiment group had a higher average mark. Okay, that's a good result. Okay, but based on the previous slide, let's ask the question: is it statistically significant, this higher average mark, or is it close enough that it could be attributed to random variation in the data? And what we see is that for 4 of the 8 results, it's not just a higher average grade, it is statistically significant. It is substantially higher, taking into account the sample size, how widespread the data is. It's not just a higher average, it is a statistically significant higher average in the experiment group. So these are the 4 assessments that are highlighted blue. So quiz 2, quiz 3, lab 1, and lab 2. For the other 5 assessments that are not highlighted blue, the results are close enough that it's a reasonable likelihood that they can be attributed to random variation in the data. But it is noteworthy that of those 5 assessments, 4 of the 5, you still have the experiment group with the higher grade. Okay, if something is completely as a result of random variation in the data, right, you'd expect about half of it, for half of them to have the experiment group higher, half of them would have the experiment group lower. That's not what we see. We see 4 of the 5 having a higher average grade, which I'd say is noteworthy. The one case where we do have a lower average grade for the experiment group, again, the results are close enough that it could very well be attributed to random variation. Now that is quite a positive result. It's not really expected, was not expected, that the experiment group would have statistically significantly higher grades for every single assessment. That would be just an outstandingly unusual result, because it's the same course, the same topics are covered, the same assessments in the same order. Results are expected to be pretty similar, with signs of a better situation for the experiment group, and that's exactly what we see. Actually, quite substantially. We have a higher average for the experiment group in 8 out of 9 assessments, and of those 8, 4 of those 8, it's not just a higher average, but a statistically significant higher average, substantially higher average. The only one case where it's a lower average, it's close enough that it could be attributed to random statistical variation. So here we have quiz 1 and quiz 2, the box plots representing the grade results. Quiz 2 is the one that had a statistically significant difference. So you can see the interquartile range extends much higher. You have a higher median, substantially higher mean value as well. For quiz 1, the maximum value is higher, but the box plots look rather similar. This is quiz 3 and quiz 4. Quiz 3 is actually the one with the statistically significant higher average grade. You see the mean value, that's where the X is substantially higher. The median is also higher. It's around 40% for the experiment group. By the way, blue is the experiment group. For the control group, the median is actually at the very bottom of that interquartile range. It's at 20%. So we have that significant difference as well. For quiz 4, the results are pretty similar, although the mean value is a bit higher for the experiment group. For the major assignment, test 1 and test 2, test 1 being the midterm, test 2 is the final. Here the results were quite close, that they can be attributed to random variation in the data. We do see the interquartile range and mean value are somewhat higher for test 2 and the major assignment. For all of these, actually, it included some topics that were covered in with quant exercises, but also a large number of topics that were not covered with quant exercises. For the 2 labs, both of them had a statistically significant difference, with the experiment group having a higher average grade. If we look at lab 1, we see the interquartile range is substantially higher, and mean value median is also higher. For lab 2, the experiment group actually did incredibly well. Not getting 100% is an outlier. So almost everybody got 100% for lab 2 in the experiment group. That the entire interquartile range is just collapsed into a line. For the control group, they did rather well as well, but getting marks 80%, 90% was typical as well for the control group, but not for the experiment group. The experiment group, almost everybody got 100. So for the labs, the topics covered also had a mix of things that were covered with quant cards, things that were not covered with quant cards. But it's interesting that with the labs, students were given a set of data, and they had to use mathematical intuition to understand and interpret this data correctly. So there's an area where that mathematical intuition really comes in. Now students were also asked questions about their experience in the class. So both the control and the experiment group were asked to rank their understanding of the course material. This is not specific to quant cards, just ranking their understanding. What we see here is the big difference is that the lower rankings, rankings 1 and 2, with 5 being the highest ranking, the lower rankings 1 and 2 received substantially less votes in the experiment group. Right? In the control group, 15% of students put their rank as 2, right? It's somewhere in 1 or 2. But in the experiment group, only 4% did that. So we have a lot less people saying that they really struggle to understand the course material. So that's a good improvement as well. Asked about their enjoyment of the material, those who ranked the highest rank, number 5, that went up from 20 to 26. The lowest rank, number 1, also went up from 0 to 1, but the second lowest rank, 2, that actually went down from 10 to 2. So we see a bit of polarization going on when we compare the experiment group to the control group, but overall there is a shift towards the positive. The high ranks 4 and 5 did go up by 3%, while the low ranks 1 and 2 went down by only 1%. So we have a more similar situation, a bit of polarization, but overall the experiment group did enjoy the course more. They recorded better enjoyment. For engagement in class, here we have polarization. Luckily, nobody put a 1 in either of the two groups. But what we do see is that when we look at moderate, less enjoyment, rank 2, the experiment group put 21 compared to 10% in the control group. But when we look at the highest level of enjoyment, number 5, the experiment group also has more, right? 14% said they really, really enjoyed, right? Level 5, the rank was their enjoyment of the class compared to 10% in the control group. And moderate enjoyment, number 4, also went up to 37 from 35. The neutral range really went down from 45% to only 28% in the experiment group. The experiment group seemed to be much more aware of whether they enjoyed the class or not. So we see this polarization where the positive ranks 4 and 5 went up by 6%. The negative ranks 1 and 2 also went up by 11%. Now, these students were not asked anything specific to quant cards in this question of the survey, but specifically the experiment group were asked some questions specifically about quant cards, and that painted a much more clearer picture. So they were asked whether exercises with quant cards improved their understanding of the course material, how they felt about that, and they overwhelmingly agreed. Some level of agreement. So here on the right you have the blue colors. This is either agree or strongly agree. On the left you have the orange colors, which is either strongly disagree or agree, and yellow in the middle is neutral. So for, did students feel that quant cards improved their understanding? We have overwhelming agreement, right? 40% agree, 28% strongly agree. Did quant card exercises improve their enjoyment of the course material? Again, overwhelming agreement, 48% agree, 31% strongly agree. Did quant card exercises improve their engagement in class? Much more clearer result than we saw in the previous graph. We have 53% say that they agree it improved their engagement, and 33% say they strongly agree, right? So we have 86% saying some level of agreement that their engagement in class was improved. Now, they were also asked more hypothetical questions about if quant card exercises were used outside of class, or outside of the exercises that they did. So course material that did not involve quant card exercises, do they feel it would have been easier to learn if it involved quant card exercises? And we see significantly more agreement than disagreement. Okay, 33% agree, 9% strongly agree. Much more agreement than disagreement. Mathematics subject matter outside of this course, would it have been easier to learn if it were taught with corresponding quant card exercises? Again, far more agreement than disagreement, right? 37% agree, 16% strongly agree. And having quant cards to use outside of the classroom, would that have assisted students in learning mathematics? So here, overwhelming agreement. We have 51% agree, 14% strongly agree. Students actually asked me, some students asked me, can they get their hands on these cards? Where can they buy them? During the study, the cards were actually not publicly sold anywhere. They are now, and I'll give you a link to where at the end of the presentation. And finally, students in both the control and the experiment group were asked to say what was their favorite topic. What was the favorite topic covered in class? If we look at the control group, which is in yellow, there were two topics that were definitely the most favorite, right? We have hypothesis testing, 33% of students said that was their favorite topic, and we have probability, 27% said it was their favorite topic. So hypothesis testing is how to look at data and be able to tell if the data supports a certain claim that someone is making or not. Probability is looking at the likelihood of various events occurring. So those were by far the favorite topics. The other topics were not that popular, except confidence intervals, which was also noticeably popular with 13% saying it was their favorite topic. Now, when we look at the experiment group, which is in blue, the two favorite topics are still hypothesis testing and probability, but other topics grow in popularity and become noticeable. We have mean, median, mode, we have percentiles, we have normal distribution that become substantially more popular. Confidence intervals becomes not as popular. And those three topics, mean, median, mode, percentiles, and normal distribution, they are all topics that were covered with quant card exercises. Normal distribution was actually that 1/5 topic that was covered with quant card exercises, but there was no corresponding quiz. So overall in the control group, 47% of students said their favorite topic was one covered with quant cards, that the experiment group covered with quant cards. Whereas in the experiment group, 68% of students listed a topic that was covered with quant cards. So what that tells us is that covering a topic with these quant card exercises increases the likelihood of that topic being listed as a favorite topic by students. And that's very significant. The results of these last three slides that really show that students feel that they enjoy the material more if it's covered with these quant card exercises, that could be more important even than a better grade, right? A better grade helps a student in that one particular course, and that's it. But if students feel that something improves their understanding of the material, they feel more confident in the material, they enjoy the material more, well, guess what? Enjoying mathematics more, that's going to help a student for the rest of their life. Okay, enjoying it more, feeling more comfortable with it, that's going to help them for the rest of their life. Right? So that's also a very positive result. So in conclusion, when we look at average grades, these are the conclusions of the study. Average grades, depending on the assessment and the topic covered, are either significantly improved for some topics, some assessments, or they're unchanged, right? Or the difference is close enough that it could be attributed to random variations. For no cases did we see a significant drop in average grades. So that's a very good result. It's the expected result as well, that depending on the topic covered, the assessment, that either there wouldn't be a significant difference or there would be a significant improvement. And that is what we see. We also saw that students in the experiment group recorded better understanding and enjoyment of the course material. Engagement was more polarized, so there was no clear result there, but students who actually experienced the quant card exercises, they overwhelmingly believe that their understanding, enjoyment, and engagement in class was improved by the exercises, and that such exercises would help them for topics that were not covered with these exercises, topics outside of class as well. And the final result, that using quant card exercises to teach a topic increases the likelihood of students ranking that topic as their favorite. And that's congruent with result number 3.